Do you know what's funny about space? When people talk about cosmic threats, they immediately jump to extremes. Black holes that will never reach us, gamma ray bursts somewhere in a distant galaxy, alien fleets that no one will likely ever see. We love to be afraid of what looks good in a trailer. And we hardly think about what might arrive quietly, without musical accompaniment, without Hollywood zoom, to Earth from outer space. 5 real threats. 5 ways the universe could seriously screw up the plans of a species that's only just begun to consider itself intelligent. And the most disturbing thing about them is that none of them look like a one-shot end of the world. They look like statistics, like infrastructure failures, like a long tail of consequences. Today, I want you to put aside everything you see in space movies for a second, and just listen to what's really on the minds of the people who are professionally trying to keep the sky from falling on our heads. Because if you ask planetary conservationists, space weather experts, and people who catalog asteroids and model worst-case scenarios what their top 5 space threats would be, the list won't look anything like a TikTok horror story. Not a supernova, not a black hole, not a mysterious object from another galaxy. Here's what's really on the short list: an undetected mid-sized asteroid that we noticed too late, an extreme solar storm that hits us at the wrong moment and destroys half the technosphere, a distant icy visitor, a long-period comet or an Oort cloud object that rolls onto the scene with little warning, a cascade of space debris around Earth that could turn near-Earth space into a minefield and strike the planet indirectly, but through the destruction of orbital infrastructure. And finally, there are rare but real astrophysical events like a nearby supernova or gamma ray burst that are unlikely to happen in the coming centuries, but are serious enough to be honestly discussed when you're thinking not only about your own life, but also about the fate of civilization. It sounds abstract until you start to develop each of these themes separately. Let's start with the most down-to-earth one, the one that doesn't require exotic physics, mysterious particles, or wild theories. The threat that lies quietly right in our orbit, in our catalogs, in our blind spots, and occasionally flashes in the news under the headline, "Asteroid will fly harmlessly past Earth." We've gotten used to the word asteroid, pictures, gray boulders, statistics, orbits. Every year, astronomical centers release reports. So many new near-Earth objects, such and such percentage of them are capable of causing regional or global damage. Such and such bodies have been tracked, such and such have not yet. This is the boring, routine part of astronomy: catalogs, light curves, diagrams. But hidden in this routine is the number one item on our list, and it looks like this: an undetected asteroid. Not a giant monster 10 kilometers across, but just a piece of rock 200, 300, maybe 500 meters across that we notice within a year, or within a few months, or maybe within a couple of weeks. It's enough that our confidence that everything is under control very quickly turns into a whisper. Are we too late? Let's arrange the dimensions. A 10-kilometer asteroid is, according to one theory, what killed off the dinosaurs. An impact that would reshape the planet's climate, biosphere, and entire ecosystem. The good news, we know almost all of these objects. The giants of the solar system have long been known. Their orbits have been calculated hundreds, and in some places, thousands of years in advance. There's no known dinosaur killer on our horizon, and that's not just advertising, but a rather boring conclusion from the data. At the other end of the scale are the small stuff, objects tens of meters across. What exploded over Chelyabinsk, what burns up in the atmosphere, leaving behind a flash, a shockwave, and a pile of broken glass. It's unpleasant, but localized. Such objects are difficult to track in advance. They're too small, too dim. We most often learn about them at the moment of the flash in the sky, and sometimes afterward from dashcam footage. But we are interested in the middle. Asteroids ranging from 100 meters to a kilometer in size. Massive enough to cause a regional catastrophe with global climate consequences if they hit land. Yet compact enough that some of them still roam freely outside our catalogs. This is where the nasty math begins. Imagine a rock the length of a city, 300 to 500 meters. It doesn't matter whether it looks like a perfect sphere from above or like a potato, pockmarked with craters. It flies in an orbit that crosses Earth's orbit every few years or decades. It's dark, coated in carbonaceous material, and reflects light poorly. It creeps up on us from the side where our night sky turns to daylight. Too close to the sun for telescopes to look in its direction without going blind. Most of the time, it exists as pure geometry, a point with coordinates we know nothing about. It's not included in our catalogs because it has never yet accidentally entered the field of view of the required survey. It doesn't glow, doesn't send signals, doesn't give itself away with flashes. In one night, some algorithm finally adds up 3 faint dots from different frames, lines them up, and asks, "Who is this?" Astronomers check, night 1. The point is here, night 2. It moved a little, a month ago, even further. We take into account the Earth's proper motion, the shift in the background of the stars, and parallax corrections. We construct a preliminary orbit, and it's gradually becoming clear this isn't just another piece of rock peacefully circling somewhere between Mars and Jupiter. This is an object whose orbit intersects Earth's orbit. And worse yet, it does so temporarily, as if it were now in the phase when its trajectory is closest to our planet. The numbers begin to add up to dates, and somewhere in the table, a line appears. Close approach to Earth in 17 months, then a clarification, plus us, a few weeks, then a new series of observations, new points, new orbital solutions. Every observation either calms you down or makes things worse. It is important to understand one thing here. The orbit itself is not a death sentence. For an asteroid to actually collide with Earth, we need 3 things to coincide. The Earth must be at the right point in its orbit, the asteroid must be passing at the same time, and the planet's gravity must pull on it strongly enough to shift its trajectory toward contact rather than safe passage. Most objects miss, sometimes by millions of kilometers, sometimes by tens of thousands. From a cosmic perspective, it's a near miss, but from a human perspective, it's perfectly safe. But here's what really scares people who consider this geometry. All physics is on our side only if we have time. The DART mission demonstrated this beautifully. A small device crashing into an asteroid altered its orbit. Not radically, not Hollywood style, just fractions of a percent. But if such a nudge had been delivered decades before the dangerous approach, it would have been enough to increase the miss from tens of kilometers to hundreds of thousands. Planetary defense isn't about huge bombs. It's about microscopic trajectory changes made early enough. If you know about an asteroid 10 to 20 years in advance, there's a chance to send a mission to it, push it, and polish its orbit until it no longer crosses our path dangerously close. If you learn about it a year in advance, your solution space collapses. If it's a month, you're almost just a spectator. Now, when you hear official statements like, "We have no known large objects on collision course for decades," there are 2 important words in them: near and known. Nearest. Because orbital calculations cease to be reliable over very large time intervals. Accumulation of small effects, gravitational interactions, uncontrolled parameters. Famous. Because anything that is not in the catalog does not exist for the models. The primary threat isn't the asteroid that already has a number, a name, and a neat orbit in the database. The primary threat is the one we don't yet know about, whether it slipped past our observations, is hidden in the sun's glare, or was simply too dim when we looked in its direction. In the reports, it sounds dry. The incompleteness of the sample of average near-Earth objects remains significant. Translated into human language, yes, there are still some things we may see too late. Why is this still not a reason to buy a bunker? Because at the same time, humanity is doing exactly what a species should do if it doesn't want to disappear from one stone. Every year, new survey telescopes are built. Algorithms for searching for faint moving objects are improved. Mission plans for deflecting potentially hazardous bodies are becoming more than just pretty PDFs, but working prototypes. Catalogs are filling up, blind spots are narrowing, early warning systems are getting better with each passing decade. But the fact remains, the top spot on our list of real space threats is not occupied by evil aliens, but by a dull, silent piece of rock that we can see not when we want to, but when physics, geometry, and the sensitivity of our telescopes allow it. And this is the first story. A rock that hits once will leave a crater, raise dust, slightly push the climate, and strongly push our self-confidence. But there's another threat that strikes differently. It has no core. It has no clear boundary. It arrives not as a stone, but as a wave of plasma and a magnetic storm. It won't leave a crater in the ground, but it could darken entire regions, shut down satellites, and rewrite the vulnerability map of civilization, which will suddenly realize how deeply it already depends on the invisible threads stretched between the planet and space. This threat comes from the most tranquil object you see every day, the quiet yellow disk with which we are accustomed to starting conversations about good mood and vitamin D. From the sun. We'll talk further about how one wrong flash on its surface can turn our technology from a superpower into a weakness in a matter of hours. Let's talk about the star we trust the most. We build our days around it. Weather apps, solar panels, Instagram sunsets, vitamin D. The sun is this warm, familiar background presence. It rises, it sets, it gives us life. And very few people consider that it is capable of something else. A blow that won't touch mountains or oceans, but can pierce the nervous system of civilization so that it temporarily loses feeling for its own limbs. If the first threat on our list is rock and momentum, the second is fire and fields. Not a comet, not an asteroid, a solar storm. Here's the thing about the sun. From our safe distance, it looks calm. A smooth golden disk, maybe a couple of spots on a good photo, a beautiful lens flare, likes under the picture. But look closer, not with your eyes, but with instruments, and you'll realize this isn't a light bulb. It's a raging thermonuclear ocean. Constant flares, emissions, magnetic loops, fields that twist, break, and reconnect. Plasma boils, rises, and falls back. Magnetic field lines are intertwined like tangled wires, and sometimes one such line breaks, and at that moment, the sun literally throws a piece of itself into space. This is a coronal mass ejection, CME. Roughly speaking, it's a bubble of plasma, charges, and magnetic field that breaks away and flies outward at speeds of hundreds, sometimes thousands, of kilometers per second. Most of these emissions go off to the side, towards Jupiter, into the void, anywhere. But sometimes in this cosmic roulette, the arrow stops on the sector, right on the line to Earth. And then things get a little more interesting. For the Earth, a solar storm isn't a lightning strike, but rather a powerful impulse that travels through all its wires. We have a magnetosphere, the planet's own magnetic field, that acts as a shield. A stream of charged particles crashes into it, deforming, trembling, and responding. Some of the energy dissipates as auroras dancing across the sky. Some escapes into the magnetotail, toward the night side. Some is converted into electric currents that flow through the upper atmosphere and, importantly, induce currents wherever large, conductive structures exist. Now remember what the modern world looks like from the point of view of conducting structures. Long high-voltage transmission lines, transformer substations, underwater cables encircling continents, rails and pipelines stretching for thousands of kilometers. And above all this is a layer of satellites, suspended above the planet like a string of beads. Sensitive electronics, solar panels, antennas, GPS, communications, weather observation, military systems, cartography, and monitoring of everything transmit data through orbit as if it were forever stable and secure. Now imagine that this entire infrastructure is caught in a magnetic storm for several hours or days of a magnitude we haven't seen since the days of telegraph lines and kerosene lamps. We already got a teaser a long time ago. In the 19th century, when electronic civilization was just learning to walk, an event occurred that is now known as a landmark, the Carrington event. The telegraph lines of the time sparked, and some devices even worked without power. The induced currents were so strong that the wires were enough to act as antennas. Auroras were seen in places where they almost never occur. It was a mild spoiler for how the sun can throw out energy. Now we have more than just a few telegraph lines. We have a global network. And the real threat isn't that one storm will kill everything. It's that a strong enough storm could strike precisely where we've become especially fragile. Satellites don't last forever. Strong radiation damages electronics, disables solar panels, and throws them off orientation. Navigation systems begin to malfunction, communications are lost, and signals become muted. What we call the cloud, data centers, servers, routers, all rely on cables and stations, which, during a strong geomagnetic storm, can experience induced currents, overheat, and emergency shutdowns. And then there's the most mundane part, grid transformers. Those gray boxes at the end of power lines aren't just pieces of metal, they're nodes, without which large regions remain without power. They can be burned down, not by a direct lightning strike, but by a slow but powerful induced current that flows from a distorted magnetic field through the ground and the lines. Changing a light bulb is easy. Replacing a large transformer requires months of logistics and manufacturing, but what if not dozens, but thousands of them fail? It's important to understand, we don't live in a Every day is on the line mode. Most solar flares are just pretty graphs for space weather experts and a few auroras for those lucky enough to see them at night. But when people who take risks seriously talk about space threats, a solar superstorm is always somewhere near the top of the list. Why? Because there's a strange balance here. The probability of a Carrington-level event in a single human generation is not enormous, but not microscopic either. The damage will not destroy the planet, but it could greatly shake civilization. And most importantly, we are increasingly tying everything we use to infrastructure, which could be damaged by such impacts. We're building more satellites, more complex networks, longer lines. We're digitizing everything: money, logistics, medicine, government services. Every year we're betting on the future of communications, navigation, and data accessibility. And every year this invisible contract with the sun becomes a little more risky. A fair question. What can we do about this anyway? You can't turn off the sun. You can't build a shield around the planet. The key here is not to try to defeat physics. It's important to learn not to be completely blind and completely fragile. We already observe the sun in virtually all wavelengths. Satellites observe its surface, measure solar wind, and monitor the direction and speed of coronal mass ejections. Space weather services issue forecasts, just as meteorologists forecast rain and storms. Yes, it's not perfect. Yes, sometimes the storm of the century is overrated, sometimes underrated, but it's better than nothing. If you know that a serious wave will reach Earth in a couple of days, you can. Put some satellites into protective modes, temporarily reduce the load on the grid, prepare energy companies for possible induced currents, warn pilots and airlines about possible communication and navigation failures. This isn't a magic shield. It's an airbag. And again, we come up against the same principle as with asteroids. Forewarned is at least not completely defenseless, but there is another, less obvious layer of threat. We're used to thinking of space weather as something far away. A news story on NASA websites, a line in a review, beautiful time lapses of the aurora borealis. In fact, this is the foundation of how resilient our technosphere will be in times of stress. If you live in a world where transactions, hospitals, logistics, water supply, and city management are tied to stable communications and electricity, then even a temporary major outage turns not into a oops, no internet, but into a chain of very mundane problems. This isn't a story about one impulse and everything shuts down forever. It's a story about how a single storm can trigger a series of problems, exposing all the weak points. Old transformers that no one was in a hurry to replace, worn out networks operating at their limits, backup systems that were once optimized for the sake of savings. Space isn't evil, it's simply providing an honest burden. And if you've built your system in such a way that it breaks with a single jolt, it's not its fault. So how real is this threat for you, sitting right now with your phone or at your computer? You probably won't experience a storm in your lifetime that burns out half your transformers and knocks out power for months, but the possibility of a very severe storm that causes significant disruptions to communications, navigation, and power grids for a couple of days no longer seems out of the realm of possibility. And the further we move into the age of total digitalization, the higher the stakes. The paradox is that, unlike an asteroid, which travels for years or decades, a solar storm is a short but sharp impact, for which we always prepare a little after the fact. We know they've happened. We know they'll happen again. We know that somewhere on the fringes of probability, there's a superstorm scenario, and all we can do is keep looking at the sun, strengthen infrastructure, don't build fragile systems that crumble from one wrong impulse. So we already have 2 items on the list: stones that fly slowly but for a long time, and which we may see too late; plasma waves and magnetic storms that arrive quickly and test the strength of everything we have suspended between the Earth and orbit. But our list of 5 threats doesn't end there, because there's another class of guests on it that we have already talked about, and which you now know by name. Unlike asteroids, which mostly hail from the inner solar system, and unlike solar storms, which come from above, these objects come from the outermost freezer of our cosmic home, from the Oort cloud, from the spherical darkness where ancient icy bodies sleep for billions of years, and every now and then one of them begins to fall inward. Sometimes it's an ordinary little comet. Sometimes it's something like 3I Atlas, a small interstellar scout, and sometimes it's a true giant like Bernard and Nellie Bernstein. And even if it's not flying straight at us, the very fact of its existence raises a question that haunts those who follow the outer reaches of the solar system. How many more of these sleeping giants are there? And what will happen if one of them one day chooses a trajectory that passes not near us, but through us? Why long-period comets and Oort cloud objects are not only a scientific gift, but also a legitimate addition to the list of cosmic threats. You know Bernardinelli Bernstein as a scientific miracle. But in any honest list of real cosmic threats, its entire family has to show up as well. Not because this particular megacomet is going to hit us, it won't, but because it's proof of concept, proof that the outermost parts of our solar system are not empty, not harmless, and not fully under our watch. When we talk about long-period comets and Oort cloud objects as a threat, we're not talking about some cinematic planet killer plunging in from the void every Tuesday. We're talking about a population of bodies so distant, so slow, and so weakly bound to the sun that even a gentle nudge, a passing star, the Milky Way's tidal pull, a cluster of molecular clouds, can once in a very great while redirect one of them inward. Most of the time, they arrive, flare a little in the inner system, and leave again. Nothing worse than a pretty comet in the sky and a few new data points in a journal. But every once in a very long time, the geometry lines up in a different way. Here's what makes long-period comets fundamentally different from the near-Earth asteroids we talked about earlier. Asteroids are mostly children of the inner solar system. They live in belts and families. Their orbits are, in a statistical sense, constrained. Most of them lie in or near the plane of the planets. Most follow similar directions, and their periods are measured in years or decades. You can build a survey designed to sweep that space efficiently. You can say with a straight face, if we keep watching this part of the sky with this sensitivity for this many years, we'll find most of the dangerous ones. Now look at the Oort cloud. It's not a disk, it's a sphere. Not 30 astronomical units like the distance to Neptune, but tens of thousands, maybe 100,000 AU across. It is, as far as we can tell, a vast three-dimensional fog of icy bodies orbiting the sun from every possible angle. A long-period comet can fall in from almost any direction, with an orbital period not in decades, but in millions of years. It hasn't been near the sun measured since before Homo sapiens existed, maybe since before mammals looked anything like us. That means two uncomfortable things. First, we do not have a stable catalog of suspects for this population. These objects spend almost all of their time so far away that they are effectively invisible. They only become detectable during the tiny fraction of their orbit when they are already falling inward. Second, because they can come from any direction, you can't just watch a narrow slice of the sky and feel safe. You're dealing with a full celestial sphere of possibilities. The result is simple. For long-period comets, warning time is not something you can take for granted. Now add energy to the picture. A typical small comet, a few kilometers across, is a spectacular object in the sky. But in terms of impact risk, it is in the same league as ordinary asteroids. But Oort cloud bodies don't have to be small. Bernardinelli Bernstein, with its 130-kilometer nucleus, is a statement. This family can produce giants. Scale up the size of a comet and three things happen at once. Its mass increases dramatically, its stored volatile content becomes enormous, and its impact energy, if it were ever on a collision course, becomes something you don't even want to visualize. Even if such a giant never hits us, its passage through the inner system can reshape things in more subtle ways. Its gravity can disturb other small bodies, its debris trail can seed meteor streams, its outgassing can create complex, dusty environments. But the key threat is not, this particular object will hit us on day X, it's statistical. If there is one megacomet, there can be more. If we found this one by digging through archival data with new algorithms, how many others are still only points of light that no one has noticed yet? And if once in some huge span of time one of these giants happens to align just wrong with Earth's orbit, the consequences would be several orders of magnitude beyond anything we plan for with normal asteroid defense. So why doesn't this keep every astronomer up at night? Because nature gave us a strange kind of mercy here. Oort cloud impacts on Earth are extremely rare on human timescales. We're talking about frequencies measured in tens of millions of years or more. If you're planning for the next century, long-period comets are a much smaller risk than the boring near-Earth asteroids or solar storms we have already discussed. But if you zoom out and think not in decades, not even in centuries, but in the lifetime of a civilization that might want to survive for tens of thousands of years, they come back into focus. The Oort cloud is a slow lottery with huge jackpots and very long intervals between draws. Most tickets are blanks, a few produce harmless sky shows, and somewhere, buried deep in the mathematics of probability, there are combinations that mean, this time you got unlucky. The honest thing to say is this: for your personal lifetime, long-period comets are more science than threat. For the lifetime of humanity as a species, they are a non-zero background risk that we barely know how to quantify. So what do we do with a risk we cannot monitor well and cannot meaningfully mitigate yet? We do the same thing we have already started doing with megacomets. We study them. Every time an object like Bernardinelli-Bernstein swings inward, we measure it in every wavelength we can. We try to understand its structure, its composition, its dynamics. We feed that into models of the Oort cloud. How many such bodies are out there? How did they form? How stable are their orbits? How often are they nudged by galactic tides or passing? Stars? This doesn't sound like planetary defense. It sounds like pure science. But on the long term, it is defense. Because the better we understand the population and dynamics of Oort cloud bodies, the sooner we might one day detect a genuinely dangerous one, and the more realistic our fantasies of active defense will become. Right now, a mega comet is more like a visiting relic from the early solar system than a live threat. It's a messenger, not a weapon. But its very existence reminds us of things that are easy to forget. That the solar system does not end at Neptune, that most of its real estate is cold, dark, and barely explored, and that the far outskirts are not a void, but simply a chapter we haven't yet reached. By now, our list of threats looks strange when compared to what you've seen in science fiction. We have rocks we might see too late, storms from our own star, ancient ice giants falling in from the dark. None of them are certain doomsday buttons. All of them are about vulnerability, where our detection fails, where our models are incomplete, where our planning horizon is too short. The fourth threat looks, at first glance, the smallest. It's not about a single big event. It's about thousands of small, man-made fragments orbiting just above our heads. It doesn't live in deep space. It lives in the thin shell of orbits around Earth where we launched our ambitions, our cameras, our networks, space debris. It almost sounds trivial compared to comets and solar storms, broken satellites, spent rocket stages, bolts, paint chips, pieces of old missions drifting aimlessly. But if you take seriously the sentence, we are becoming a spacefaring civilization, then orbital debris stops being a trifle and turns into the fourth item on our list. Here's the uncomfortable geometry of low Earth orbit. To put a satellite there, you don't just lift it up, you accelerate it sideways, hard. Most satellites in low Earth orbit move at something like 7 to 8 kilometers per second. That's orbital speed. It's what keeps them falling around the Earth instead of falling back down. Now, imagine two objects in similar orbits colliding. They're not gently bumping. They're hitting each other with relative velocities of several kilometers per second. At those speeds, almost anything becomes a weapon. A flake of paint can crack a window, a bolt can punch through a radiator, a piece of metal the size of a fist can slice through shielding, cables, fuel lines. When two satellites collide, they don't just break. They fragment. Hundreds, thousands of pieces scatter along their orbit, each piece now a potential impactor for something else. This is the core of what's sometimes called the Kessler syndrome. The idea that beyond some critical density of objects in orbit, collisions start triggering more collisions. A chain reaction that fills certain orbital bands with so much high-speed debris that they become effectively unusable for years or decades. You don't need an evil plan for this, you just need enough traffic and enough time. Why is this a space threat and not just an engineering problem? Because our relationship with near-Earth space is changing. 20, 30 years ago, orbit was the realm of a handful of space agencies and a few large military and communications platforms. Now, constellations of thousands of satellites promise global internet coverage. Earth observation fleets watch weather, crops, forests, ice sheets. Navigation systems let planes land, ships sail, cars drive, phones find themselves. Scientific telescopes float above the atmosphere, watching everything from lightning to distant galaxies. Our picture of the planet's climate, our ability to monitor disasters, our timing systems for finance and communication, All of that is quietly anchored in those beads of metal and silicon moving overhead. If low Earth orbit were to become a shooting gallery of uncontrolled debris, we wouldn't lose the sky. We'd lose a significant chunk of our ability to see and coordinate what happens below. No GPS, no global, low latency communication constellations, less weather data, less early warning for storms, fires, floods. Less monitoring of illegal fishing, deforestation, emissions. The threat here is indirect but very real. Not from space hitting us, but from us making near-Earth space so hazardous that we cut off ourselves from a crucial layer of modern infrastructure. The irony is that we already know how to avoid the worst-case versions of this scenario. We know how to design satellites that deorbit themselves at the end of life. We know how to coordinate launch slots and orbital shells. We know we should avoid deliberately blowing up satellites in low orbit in anti-satellite tests that create clouds of shrapnel. But knowing and doing are different verbs. Space is becoming commercial. Launches are cheaper. The temptation to fill the sky now, clean up later, is strong. Regulation lags behind expansion, and the physics doesn't care whether a piece of debris came from a prestigious space agency or a budget CubeSat. If enough accumulate junks in a popular orbital band, and if one bad collision or one irresponsible test creates a dense debris cloud, we might find ourselves in a world where launching through that shell becomes much riskier. For a civilization that is just starting to rely on space as heavily as we once began to rely on electricity, turning parts of orbit into a minefield is, to put it mildly, a bad idea. This is why orbital debris belongs on a list with asteroids, comets, and solar storms. It's the only threat on our list that we create ourselves. And that makes it the most controllable and simultaneously the most shameful if we still allow the worst case scenario to happen. 4 threats: stones we might see too late, storms from our own star, ancient giants falling in from the dark, fragments of our own ambition, turning our doorway to space into a hazard zone. The 5th is different. It doesn't care about our orbits, our telescopes, or our level of technology. It comes from far beyond the solar system. And in an honest conversation about cosmic risks, it's impossible not to mention it, even if the likelihood of encountering it in the coming centuries is negligible. I'm talking about rare, high-energy astrophysical events, nearby supernova and gamma-ray bursts. No, there is no star tomorrow that is going to explode so close that it sterilizes Earth. There is no signal that a directed death ray is already flying towards us. But on the scale of millions of years, the galaxy is not a quiet place. And if you're making a list of not only what might actually happen on your shift, but also what defines the general rules of the game for life in space, those events should be somewhere at the bottom of the page, circled, because they remind us of one simple thing. Sometimes the universe plays a game in which we are not even participants. We are simply sitting on a planet that happened to be in the right or wrong place when the next round began. And we'll talk further about what the words nearby supernova and gamma ray burst actually mean for a planet like ours. Not in the style of headlines, but in the style of honest physics. When people hear supernova, they picture fireworks. A star swells, brightens, explodes in a spectacular flash. Some gorgeous Hubble image with neon colors and poetic captions. It looks like art, like something you'd hang on a wall, not something that could ever hang a threat over an entire biosphere. From a safe distance, that's exactly what a supernova is. An incredible show, a forge for heavy elements, a reminder that stars die so that planets and people can exist. From the wrong distance, it's something else. Here's the basic idea. A massive star spends millions of years burning fuel in its core. Hydrogen to helium, helium to heavier elements, fusing its way up the periodic table while gravity pushes inward and pressure pushes outward. At some point, it runs out of fuel that can support the core against gravity. The balance breaks, the core collapses, the outer layers rebound, and in a fraction of a second the star does something it's never done before. It dumps an enormous amount of energy into space, in every direction, across the electromagnetic spectrum and in floods of neutrinos. If you're very close, you don't get a light show. You get a sterilization event. Intense radiation slams into any nearby planet's atmosphere, breaking molecules apart, shredding ozone, triggering chemical cascades, cosmic rays spike. For anything living on that planet's surface, the environment can shift from mostly fine to deeply hostile on timescales that don't respect evolutionary pacing. The good news, space is big. The radius within which a supernova is truly devastating is measured in tens of light years, not hundreds or thousands. The bad news? On a galactic timescale, stars do sometimes explode that close to somebody. We just don't want that somebody to be us. There's a similar story with gamma ray bursts, GRBs. These are among the most energetic events we know of. Narrow beams of high-energy photons launched when certain massive stars collapse or when neutron merge stars. If one of those beams were pointed directly at Earth from the wrong distance, it wouldn't look like a cool sci-fi laser. It would look again like atmospheric chemistry getting punched in the face, ozone depleted. UV flux at the surface rising, ecosystems stressed from the bottom up. Phytoplankton, plant life, everything that relies on a relatively gentle radiation environment. But there are two big pieces of sanity you need to hold on to while we talk about this. Most supernovae and GRBs we observe are very far away. They are lights in other neighborhoods, not grenades in ours. We don't have a known ticking time bomb star sitting 10 light years away, about to explode any day now. If you're looking for something to ruin your week, a missed asteroid in a bad orbit or a nasty solar storm are still far more realistic candidates. So why are we even putting these events on the list? Because when you zoom out far enough, they are the background dice rolls that set the long-term odds for life in the galaxy. And they teach a lesson that quietly connects all 5 threats we've talked about. Imagine you could rewind the history of the Milky Way and play it again and again. Same laws of physics, same distribution of gas and dust, but tiny differences in initial conditions. Sometimes, a massive star will form a little closer to where a young Earth-like planet is orbiting its star. Sometimes it will form a little farther. Sometimes a gamma ray burst beam will sweep through a region, just after a biosphere has gotten started. Sometimes it will miss. On one run, life on some world thrives uninterrupted for billions of years. On another, it gets hammered, reset, pushed into blind alleys, or total collapse by an event that has nothing to do with its own behavior, and everything to do with bad cosmic timing. That's the uncomfortable part. In this game, you don't even know you're playing until after the outcome has already been written. From Earth's point of view, we may already have lived through distant echoes of such events. Some researchers have suggested that certain extinction patterns or isotope anomalies could be signatures of far-off astrophysical blasts. Others argue for more mundane explanations. The point is not that a supernova definitely killed the dinosaurs or a GRB wiped out some ancient ecosystem. The point is that the galaxy is noisy, and once in a very long while, that noise can reach across space in a way that matters to little blue planets. If this all sounds abstract and unhelpful, that's because, in a sense, it is. You can't build a deflection mission for a supernova. You can't armor a planet against a gamma ray burst. You can't file a complaint when a star 100 light years away decides it's time to end its life violently. So from the perspective of practical planning for the next century or two, nearby supernova and GRBs are more like boundary conditions than actionable threats. They tell us we are not in a perfectly safe, static universe. Long-term habitability is shaped not just by orbits and atmospheres, but by rare, high-energy events. On million-year timescales, the galaxy throws curveballs. From a scientific point of view, we watch them for what they reveal, how massive stars die, how elements heavier than iron are forged, how jets are launched, how extreme physics behaves. From a philosophical point of view, they're a reminder. We are not the main characters in every story the universe is telling. We are local protagonists in a much bigger narrative. So now we have our 5. Let's lay them out one more time, not as clickbait, but as an honest inventory of how space can hurt, or at least seriously stress, a civilization like ours. And 1. Undetected medium-sized asteroids. Not the dinosaur killers we already know and track, but the hundreds of meters class that are big enough to cause regional devastation and climate perturbations if they hit, yet small enough that some of them are still missing from our catalogs. The threat? Seeing them too late to do anything but watch. 2. Extreme solar storms. Coronal mass ejections and flares align just right with Earth, dumping energy into our magnetosphere and inducing currents in our grids, damaging satellites, disrupting communications, navigation, and power. The threat, discovering how fragile our technological nervous system really is. 3. Long-period comets and Oort cloud giants. Rare visitors from the deep freeze at the edge of the solar system. Most are harmless, some are gifts to science, but in the statistical tail lurk trajectories that cross our orbit and sizes that make impact a word you never want to see in the same sentence. The threat, a very slow lottery with very large tickets and very long odds. 4. Orbital debris and Kessler-style cascades. Not nature's fault, but ours. Fragments of spacecraft and rockets, cluttering near-Earth space, raising the risk of collisions that generate more debris, with the potential to compromise or temporarily deny the orbital infrastructure we've come to depend on. The threat, sawing at the rungs of the ladder we're climbing into space. 5. Rare, high-energy astrophysical events, nearby supernovae and gamma-ray bursts, unlikely on human timescales, but powerful enough, in principle, to alter atmospheres and biospheres from afar. The threat, the reminder that some risks are set by the cosmic environment long before we arrive. Individually, none of these is a guaranteed doomsday. We're not living in a constant, imminent countdown. Collectively, they paint a different picture. A universe that is not actively hostile, but casually dangerous. A place where long-term survival is not a given, and where ignorance is a much bigger enemy than any particular rock or flare. Here's the twist that makes all of this more than just a horror anthology. For 4 out of 5 threats on that list, our situation is getting better over time, not worse. We're finding more asteroids every year, pushing down the number of dangerous unknowns. We're building better solar observatories and starting to take space weather seriously. We're learning to read the outer solar system, tracking visitors like Bernardinelli Bernstein with tools unthinkable a generation ago. We're finally, reluctantly, talking about space traffic management and debris mitigation. Even our understanding of supernova and GRBs is improving. We know which nearby stars are candidates. We can say something about distances and directions and probabilities, instead of just shrugging at the sky. That doesn't erase the risks, but it changes the role we play. We're no longer just passengers on a rock, hoping the universe doesn't notice us. We're beginning to act like crew. Crew members can't stop every storm, but they can map the icebergs, reinforce the hull, learn which routes are safer, and fix the wiring before it fails at the worst possible moment. If you strip away the fear and the drama, cosmic threats are just the sharp edges of reality. They're the parts of the universe where our models are still thin, our detection is still patchy, our planning is still too short. Talking about them honestly isn't about scaring you into paralysis. It's about the opposite, showing that almost every scary phrase you hear, killer asteroid, solar superstorm, gamma ray burst, has a second half to the sentence. And here's what we're doing about it. The story of the next century is not going to be, we got hit by everything on the list. Much more likely, it will be about small, real tests. A close pass by an asteroid we saw in time, a solar storm that knocks out part of the grid, but not all of it, a debris incident that finally forces serious cleanup. And if we're paying attention, those tests will push us to build a civilization that is less brittle, more alert, and more honest about the universe it lives in. We can't negotiate with physics, but we can learn its rules well enough to stop being surprised by every card it plays. Space is not out to get us. It just doesn't care either way. And that, in a strange way, is good news, because it means that what happens next depends less on whether the universe is friendly or hostile, and more on how seriously we take the fact that we are the only ones who can make our planet a little less fragile under this sky. Let's do something different for a moment. Up until now, we've walked through the 5 big cosmic threats like an engineer walking around a machine. We pointed at components, listed probabilities, talked about models, orbits, energies, catalogs, plasmas, and cross-sections. That's useful. It gives structure. But stories don't live inside neatly labeled diagrams. They live in the messy overlap between equations and people, between impact probability and what actually happens on a Tuesday afternoon when that number refuses to drop to 0. So instead of inventing a 6th exotic catastrophe or dragging out black holes for the sake of drama, let's stay with the same list: asteroids, solar storms, distant, comets, orbital debris, and rare astrophysical flares, and try to go through some of them as if they weren't graphs, but days that someone actually lives inside a newsfeed, inside their apartment, inside a system that's accustomed to considering space a backdrop, not a risk factor. Imagine a typical morning, so typical it almost dissolves. You wake up, pick up your phone, automatically check your notifications, and scroll through the news. At first, you don't even notice anything has changed. The feed is just another feed. Politics, sports, someone's scandal, someone's joke. And only a couple of minutes later does your eyes suddenly catch a headline that was already somewhere in the background, but your brain had filtered it out as just another science for show. NASA announces new near-Earth asteroid. Impact risk extremely low. You don't click right away because such news pops up regularly, the same old pattern. They found the object, calculated its orbit, reassured everyone, saying that there's no danger, we're just monitoring. And yet, throughout the day, this story doesn't go away. It's repeated on various websites, pops up in Telegram channels, appears in the main news feed, and is retold by that same relative who usually reposts anything that sounds nervous. At some point, you finally open the article and see the bare details. A new object, a couple of 100 meters long, with a newly confirmed near-Earth orbit, found in a previously obscured area of the sky. Behind the complex letter and number notation is a rock the size of a small city, and at the very bottom of the text is the familiar formula. The probability of a collision is extremely low. As the orbit is refined, it will likely become zero. There is no reason to panic. You close the tab, return to your daily routine, and almost nothing changes. In your world, but somewhere in the mission control center, in the labs and catalogs, in windowless rooms with rows of screens, everything has already shifted from routine. There are people who are urgently booking time at telescopes, retrieving archives of past observations, trying to find faint traces of the same object from months or even years ago, to stretch the data arc and improve the orbit. They run algorithms that sift through thousands of possible trajectories, taking into account the gravity of all the planets, solar radiation pressure, even minor effects. Each new set of coordinates slightly shifts the estimate of future encounters, and on one of the screens there is that line no one likes to see: the date, time, and distance of a potential close pass near Earth, plus in the right column a small, but not yet vanished, percentage of non-zero impact probability. A week passes and the news returns, in a different tone. Now it's not just about extremely low probability, but also about a narrow corridor of uncertainty that cuts across the world map like a thin ribbon, passing over oceans, land, and familiar cities. On-air commentators repeat the same tune. Almost certainly a miss, but as the orbit is refined, the risk will decrease. We've seen this many times. Sometimes this actually happens. A new series of observations dramatically reduces the range of possible trajectories, the corridor shifts, the collision probability drops to practically zero, and the object is peacefully added to the list of those who almost scared but didn't. However, it's enough to imagine that in some iteration, this won't happen. The probability doesn't reset to zero, but rather gets stuck at an unpleasant level. Not catastrophic, but at a level at which the question ceases to be purely academic. Then the scenario's center of gravity instantly shifts from astronomers to engineers, military personnel, politicians, and economists, because questions need to be answered. How much time do we have? What missions can we realistically launch? What are we willing to risk to change this orbit? Where will the surface hit if we do nothing? Who decides whether action is better than watch and hope? The physics of an asteroid threat is mercilessly simple. Mass, speed, angle of entry, density, composition. If a rock hits, the consequences will be determined by these parameters and the geography of the impact point, regardless of how many broadcasts we've run or what hashtags we've used. But humanity is complex and uneven. Some will demand a strike mission at any cost. Others will argue that the risk is less than the cost of failure. Some will think about global security, others about ratings and elections. In the best case scenario, the story ends with a quiet victory. 10 years before a dangerous approach, they managed to launch a mission to the asteroid, slightly shift its orbit with a kinetic impact. A decade later, the asteroid passes at a safe distance, and only a line in the impact risk removed catalog reminds us that the probability curve was once creeping alarmingly high. In the worst case scenario, the launch is delayed. Launch windows are missed, countries fail to reach an agreement, and the world suddenly finds itself in the position of spectator, with not only the date of the solar eclipse marked on the calendar, but also the moment of atmospheric entry of a specific object. The impact will affect most of the planet only through news and climate change. A relatively small region will experience it as light, sound, a shockwave, and a new crater on its map. With a solar storm, everything looks completely different, and that's what makes it especially insidious. There's no rock in the road, no black trail across the sky, no image for the imagination to grasp. It all begins with the almost amorphous graphs at solar observation centers. A sharp burst of X-rays, a complex structure and images of an active region, a coronal mass ejection shooting out into space like a huge bubble of plasma. And someone watching this sequence of frames draws an imaginary line through this expanding cloud and realizes that the Earth's orbit falls within its cone of expansion. This is followed by dry space weather bulletins, warnings for satellite operators, recommendations for airlines to reconsider high-latitude flight routes, letters to energy companies urgently requesting that they be prepared for geomagnetic disturbances. To the average person, all these layers remain invisible. The most they see is a short note, major solar storm expected, experts say impact likely limited, which, in the daily news noise, competes with exchange rates and the latest scandal. Meanwhile, the details on which everything depends are stored within the ejecta itself, the orientation of its magnetic field relative to Earth's, its precise speed, the structure of the front. If the field is deployed poorly, if it connects with ours in such a way that the energy merges maximally efficiently, the impact on the magnetosphere will not just be a flash of beautiful auroras, but a real onslaught, capable of generating strong currents in the upper atmosphere and, as a result, induce currents wherever we have long conducting systems. When the front reaches Earth, those living at a sufficient latitude may initially notice only magic. Northern lights appear where they have never been seen before. Green and red curtains stretch over cities. People pour out into the streets, filming videos, writing enthusiastic posts. Meanwhile, in orbit, some satellites switch their equipment to safe mode, adjusting their orientation to minimize the particle flow. Others begin to experience problems, detector spikes, memory glitches, electronic errors. The heated and expanded atmosphere increases, dragging low orbits drop slightly, and operators waste fuel on corrections, which they might want to save for calmer times. On the surface, currents induced in power lines begin to stress transformers beyond their intended capacity for long-term operation. In some places, protection systems operate perfectly. Circuit breakers trip, the load is redistributed, and part of the network is controlled to shut down. Elsewhere, old overloaded components begin to fail. One large transformer burns out, another follows, and the chain, designed to be resilient, reveals that its resilience has long been an illusion. For an individual, this manifests as a web of short and long outages. Lights flicker, internet goes down, GPS signal fails, flights are delayed, ATMs are temporarily unavailable, and navigation displays are erratic. If a region is sufficiently vulnerable, the restoration time for some components is measured not in minutes, but in weeks, because a large power transformer is not a component that can be picked up from the nearest warehouse. It is a massive, expensive object with a long production cycle. After such a storm, there will be reports, commissions, standard revisions, and debates. Some will say that overall, everything went well, because we avoided a global grid collapse. It was a valuable lesson. Others insist that we were dangerously close to an uncontrolled cascade failure, and only chance and the heroism of individual operators prevented the worst. The next time the conversation turns to infrastructure upgrades, backup generators, and grid modernization, this storm will either be a pro or be remembered as a strange week that will be forgotten in a couple of years. The sun doesn't have the choice. We do. With distant comets, oddly enough, there's more philosophy than panic, at least in the coming centuries. In most scenarios, they come to us as ambassadors from the icy fringes, not as projectiles. A distant, faint object appears in survey data, an orbit is constructed from several weak points, it becomes clear that the trajectory passes far from Earth, and attention shifts from the question of, is this dangerous to us, to, what does this tell us about the early solar system? In the future, when surveys like Vera Rubin's run for decades, and the archives are riddled with algorithms that detect any slow motion against the background stars, such long-period visitors will appear on our maps more often. We'll see not just isolated, strange giants, but a whole spectrum of sizes and orbits, from which, like statistics, we can derive estimates of the actual number of such bodies in the Oort cloud. One or two will make the news as the comet of the decade, while the rest will remain the preserve of a narrow professional audience. And yet, the very fact that giants like Bernard and Nellie Bernstein are perched in this cold cloud, tens of thousands of astronomical units from the sun, forces us to consider another possibility. What if one day one of them turns out to be not just a passing visitor, but has a trajectory that intersects the Earth's orbit? The probability of this is so small on human timescales that it would be unfair to frighten a specific generation. But on a scale of millions of years, it is one of those cards the universe holds in its deck. The answer to such a possibility will not be eternal anxiety, but a long, slow, centuries-long process. The creation of comprehensive maps of distant regions, missions to comets, the development of engines capable of not only catching up with, but also towing massive bodies. Eons will pass before we really need such things. But between we know nothing at all and we know how to meet such guests consciously, there is a long way, which begins now with every observation, every spectrum, every orbit added to the catalog. Orbital debris is a far less grandiose story, but no less revealing, because here the evil genius isn't even space itself, but ourselves. To put a satellite into low orbit, it's not enough to simply lift it up, it needs to be accelerated along it to an orbital velocity of about 7 to 8 kilometers per second. At this speed, everything orbiting the planet possesses colossal kinetic energy. If two objects collide at even the slightest angle, they transform each other into a cloud of fragments, not neat pieces, but tiny shrapnel flying in all directions, each particle carrying the same breakneck speed. A single unfortunate impact between two large satellites or upper stages can generate thousands of dangerous fragments. These fragments, scattered along the orbit, begin to intersect with the trajectories of other spacecraft, increasing the likelihood of further collisions. At a certain density of objects, the risk of a chain reaction, as described by Kessler, arises. One accident gives rise to several, which then give rise to dozens, and the entire specified altitude range turns into a hostile environment, which is not so easy for a new device to penetrate without taking a hit. We currently live in the pre-Kessler era, still with a large reserve of freedom. But already, thousands of operational satellites and tens of thousands of trackable fragments are in orbit, not to mention millions of smaller ones, too small to be routinely counted, but large enough to destroy a spacecraft on impact. If we launch several more mega constellations of tens of thousands of satellites into this system, add to that a couple of irresponsible anti-satellite tests, and season it all with the lack of strict global regulations for the mandatory disposal of spent satellites, then it won't take any space villain to create orbital ranges in a couple of decades that will become too risky to access. And this will be a threat not to life on Earth, but to our own expansion beyond it. The loss of reliable access to low orbit would mean a blow to communications, navigation, weather monitoring, climate and disaster monitoring, and scientific missions. It's as if we're sawing off the very steps of the ladder we want to climb. This threat is particularly troubling, precisely because it's largely unaffected by physical limitations. We can stop conducting destructive tests, we can require operators to ensure deorbiting of spacecraft at the end of their service life. We can invest in active debris removal technologies. All of these are political and economic decisions, not the will of the sun or the whims of gravity. And if we cut corners here, the blame will be entirely ours. The most distant threat, nearby supernova and gamma ray bursts, is the least amenable to dramatization in the morning, man, phone, news format, because if such an event occurs at too close a distance and in an unfavorable geometry, it won't leave us much time for reflection. Therefore, it sounds less like a plotline for the coming centuries than like a line in the margins of a map. Rare, unlikely, but physically possible. It's at the very bottom of the list of real threats for the near future. But it can't be completely ruled out, because it's precisely such events on a galactic scale that define the boundaries of the comfortable zone for life, where billions of years of undisturbed development can occur, and where a burst occurs once every few million years, radically altering conditions. Taken together, the list is a strange one, not unlike that of a cinematic disaster. Asteroids, which we're mostly learning to see in advance, but still dread, missing a few average ones. Solar storms, which rarely reach truly extreme levels, but can catch us at any moment at the height of our technological dependence. Distant ice giants, a reminder of the scale and depth of our cosmic home. Orbital debris as a mirror of our own irresponsibility. And the rare explosions of distant stars, which set the background level of galactic risk. None of these phenomena lives in a "it'll all be over tomorrow" mode. Together, they paint a picture of a universe that is neither hostile nor friendly. It's simply indifferent. And the only place in this story where intention, planning, and responsibility appear is in us. The most interesting thing is that the situation on 4 of the 5 points has been slowly improving over the past decades. We are indeed closing holes in asteroid catalogs, increasing the sensitivity of surveys, building new telescopes and trajectory deviation testing missions. We've begun to take space weather seriously, deploying observation satellites and implementing protocols for networks and operators. We've only just begun to study distant, giant comets and are already planning surveys that will transform them from exotic objects into statistics. We've begun, albeit tentatively, to discuss orbital behavior and the need to clean up after ourselves. Even about supernovae, we know more than ever which stars have the potential to become hazardous, at what distances they are located, and how often such events occur in the galaxy. This doesn't eliminate risk, but it does change the observer's role. We cease to be mere passengers on a rock hurtling through all this as it happens, and gradually become a crew. A crew can't prevent storms from raging in the ocean, but they can learn to read the skies, strengthen the hull, avoid icebergs, update charts, and repair wiring before a short circuit coincides with a wave. Threats from space, stripped of their sensationalist sheen, turn out not to be horror stories, but a harsh version of feedback. They show where we are still blind, where we are building too fragilely, where our planning horizon ends with the next reporting quarter when it should extend a little further. The universe isn't trying to kill us, but it's not going to save us either. This, oddly enough, is a huge plus. It means that the fragility or resilience of our civilization under this sky depends not on the whims of the sun or the arrival of another giant rock, but on how seriously we take the fact that we live not in a stage set, but in a real, dynamic system full of rocks, plasma, ice, radiation, and long, slow processes that don't conform to the human calendar. The sooner we stop seeing space as just a pretty backdrop and start perceiving it as part of our environment, the better our chances of ensuring that the next time the sky throws up a challenging scenario isn't the day it all ended, but the day we first realized we were ready.